Hello. Today I would like to present to you the lift estimation using physics-informed neural network on a bird-scale flapping wing vehicle. We see that UAVs and planes have well-known dynamics modeled for decades now. On the left, we see a quadcopter-like vehicle flying with propellers, and on the right, we see glider plane gliding with high aspect ratio wing. Naturally, the question would be, what kind of dynamic model will we choose if there is very little known information about the platform? Here are the motivating questions for this study. Question 1. Are there existing literatures that could inform us about the complex aerodynamics of a flapping wing vehicle? Question 2. Could we leverage any machine learning techniques and accurately predict lift during flight given some known features? And that leads us to a physics-informed neural network, or short for PINN. The experimental platform GEMIS is constructed as part of a research project for my PhD studies and will be used in this class project for collecting lift force data. Here's a flapping platform mounted on an ATI mini force reducer. After capturing over 20 seconds of flight data, which corresponds to 60 flapping cycles, we use the Butterworth filter with a passband frequency of 30 Hz to smooth out the data so that the high frequency and noise can be correctly filtered out. Filter lift force Fc and flapping angle theta versus time over selected 4 flapping cycles are shown. It is clear to see that the BFWV platform has a faster downstroke and slower upstroke, with a maximum upstroke angle of 30 degrees and a minimum downstroke angle of -20 degrees. Shown in circles are the stroke reversal. Blais-Elman method is a widely popular method used in the realm of aerodynamics. First, we'll formulate the analytical solution to the lift force estimation. In the equation shown, ρ denotes the air density, Cl denotes the coefficient of lift as a function of the angle of attack alpha, theta dot denotes the angular velocity of the flapping wing, and r denotes the span-wise location, and finally, C of r denotes the chord length at the span-wise location r. To calculate total lift, a Riemann sum is performed over the span of the whole wing profile. As shown in the above figure, we see that the estimated lift using the above-mentioned Blais-Elman method is able to capture the upstroke and downstroke phases of the BFWV platform really well. However, it fails to recognize the zones where the BFWV is not producing lift and tends to underestimate the total lift production. Therefore, we would like to propose the following physics-informed neural network by employing residual learning. This PINN-based approach will learn the error between the actual lift and the estimated lift. Most importantly, a bidirectional RNN network will be used since the BFWV flapping aerodynamics is highly nonlinear and unsteady. The lift generated at the current cycle heavily depends on the lift generated from the turbulence and vortices created from the previous quasi-steady stroke phases in the form of wake capture. This is specifically useful in the context that we have access to the entire time series of data points, since it will be able to better predict the lift forces. However, this would not be too useful during a real-time reinforcement learning application, since it would not have future data points available. Next, we'll use a leaky ReLU activation instead of a traditional ReLU. The key reason is that the traditional ReLU has a dineuron problem. It exemplifies itself in a case when the analyzed data is mostly periodical and zero mean. The traditional ReLU would tend to pick the safest option, which results in a zero mean force production. And finally, the loss function shown in the rep box is used. The result of the implementation of the above-mentioned PINN algorithm is shown in the figure above. It is clear to see that this model is able to capture the upstroke and downstroke trends really well. In addition, we see that the proposed PINN model is able to predict the zero lift Fz equals 0 region much better than the physics model. After analyzing the frequency of the estimated lift force, shown in green, we see that the frequency of 3 Hz which perfectly matches with the measurement data. However, we also see a key limitation of the proposed algorithm. The peaks of the model seems to lag behind the peaks of the measurement data, which means that it is implying an earlier downstroke cycle than in actuality. I believe this could be further improved by using a time series stamps of the peaks of the measurement data as a feature as the input to the PINN model.